Okay, so this is slightly off topic of this conversation, of this meeting, but I'm afraid it's what we've been doing, so it's what I have to talk about. So what I'm going to do is, first of all, for those of you that are not used to active pneumatics, give you an introduction to active pneumatics, and then I'll talk about going from 2 to 3 dimensions, and then look at 3 dimensions, and in particular talk about shape changes. And what I want to say is that maybe what we're seeing in these active systems may be relevant to shape changes in biology. So this is the sort of system that we're looking at. Dense active systems, for example, a dense layer of bacteria. And what you see in 2 dimensions is this state which looks like turbulence, which has now become known as active turbulence. Perhaps in bacteria, which are pneumatic-like shapes, you'd expect this to be described by a pneumatic theory. Perhaps more unlikely is that you can look at systems like this one. I'll get that one to move, yes, which are epithelial cells on a substrate. And again, you see active pneumatic-like active turbulent behavior. And that's perhaps more unlikely because these systems, these cells are on average round, and therefore it's surprising that they take a pneumatic shape. So one of the big questions is to look at these systems and actually see to the extent to which they can be described as active pneumatics. Now, the way these are described is by continuum equations of motion, which start off looking like the equations of motion of pneumatic liquid crystals. So here is the equation, just in outline. Q is the order parameter of the liquid crystals. Q is advected by the flow and then rotated by shear flows. And then the system relaxes to a minimum of a free energy, which means that in equilibrium, it's in a pneumatic state. Here's the equation for the velocity. The way I've got it written, it looks very like the Navier-Stokes equations with a stress tensor here. And this includes viscous stress and an elastic stress, which takes account of the molecular structure of the liquid crystal. And these equations are very well known for passive liquid crystals. To describe active liquid crystals, you have to add a term which takes account of the flow fields produced by the active particles, by the bacteria or by the cells. And that term takes this form. It's equal to some strength of the activity times the pneumatic Q tensor. And it looks like this because this reflects the symmetry of the flow field. The important thing to note is that this comes in the stress. It comes under a derivative. And so any gradient in the order parameter, for example, at a topological defect, is going to give you stresses and it's going to give you flows. The other thing that this term does is that it destroys the pneumatic ordering. In these active systems, there is an instability to any fluctuations in the directive field. And so you lose perfect pneumatic order. And what you get instead is this active turbulence. Now, later on, I'm going to talk about 2 different sorts of activity. One which corresponds to a positive zeta, the strength of the activity is positive. That corresponds to extensile flow fields, where one of the pneumatogens pushes fluid out along the ends and pulls it in along the sides. This sort of system is unstable to bend perturbations in the pneumatic directive field. Or for zeta is negative, I'm going to talk about a contractile system, and these are unstable to splay perturbations. So it gets you one way or the other. So this is what we have, is the microswimmers. Here's the microswimmers there. And you can see that this active turbulence is a highly vortical state, lots of swirling around. If we solve the equations of motion, we get what's happening over here. And what you see is these yellow jets of fluid. This is the velocity field. These yellow jets are regions of high velocity. And underneath is a vorticity plot, again, from solving those equations of motion. And you see you get regions with high vorticity. I think the red's anti-clockwise and the blue is clockwise. And typically this vorticity length scale is about 5 to 10 of the bacteria. So this is a nematic liquid crystal. Nematics have topological defects in 2 dimensions. Typically they're +1/2 and -1/2 topological defects, where the director field looks like this. And if in a passive system, what you expect is that these things destroy each other in pairs, and this is indeed what happens in an active system as well. But the extra thing you get in an active system, those two are going to destroy each other, is that around here, I think, topological defects pop out in pairs, and you get new topological defects formed. So you get a gas of these things which are continually being destroyed and reforming. And in particular, the +1/2 defects are self-propelled. That just follows from this idea that, that any sort of gradient in the director field definitely has loads of gradients around a defect, gives you stresses, give you flows. And so this is going to set up a flow field. And because of the symmetry, the polar symmetry, that's going to be an unbalanced flow field. And this thing is going to move, and it actually moves towards its head. So this is a summary of what's going on in these active systems. And in 2 dimensions, people really understand pretty much what's going on, understand it, but don't really have a proper theory in theoretical physics language which can mathematically describe what's going on. So that's 2 dimensions. So now let's think about what might happen as we move to 3 dimensions. And first thing to say is thank you very much to Liam Rusker and Marana Nejad, who are the people who did all the hard work to do this. This work is very much up to them. Let me start with 3 biological examples which explain why we might care about active systems moving from 2 dimensions to 3 dimensions. So this is the first one, experiments done by Paul Guillemat and the Geneva group. What they did is they put cells which are slightly elongated before you start, so nematic shaped cells, on a small disc. And then the cells divided to fill up the disc. As they divide and as they reach confluence in the disc, they start circulating around, they start moving around. Somehow the activity has to sort of go somewhere, the energy they're making. They have this collective motion. And then if more cells are formed, what happens is that these things move up and grow into the 3rd dimension, like a witch's hat. And so you get this sort of nice shape here. Another one where things move into the 3rd dimension, and this is from some of our own work, is things called Pseudomonas. And Pseudomonas are bacteria which move on a surface, and they move by twitching their feet. And sometimes in these fast-moving bacteria, what you find is that you get patches where the bacteria are verticalized, where they stand up perpendicular to the surface. And it turns out that what sets these off is topological defects. In particular, 2 +1/2 topological defects, shown in here in orange, move towards each other. And then they sort of start circulating each other because they're repelling each other. So they end up almost orbiting each other. That sets up flows which push the bacteria to stand up. And if this pushing is hard enough, you end up with a little gang of verticalized bacteria, and other bacteria come to join them. So you get this whole region of bacteria standing up. And if the movie will go, this is this thing really happening in real life. Here you can see one of these colonies forming. Those are reasonably simple examples. What we're working towards, this really, really complicated setup, is morphogenesis, and in particular, the early stages of morphogenesis, gastrulation. Somehow, animals and plant, everything has to get from a tiny egg, where on the whole cells are in a layer around the outside of the egg, to a much more complicated three-dimensional structure. And gastrulation is the beginning of this. You get a series of cells forming, which are differentiated, which are special. And then you get invagination. And so the system ends up with different layers, and the different layers will eventually form the different organs of the body. And no one's quite sure, I think, whether it's physics or whether it's biology which does this. It's probably actually a mixture of the two. But if you look at gastrulation forming in this movie in the chick embryo, what you can see is large-scale flows. These flows take place over significant fractions of a millimeter, lots of cells moving together to form this invaginated region here. And so how on earth does this cell organize itself to get from 2 to 3 dimensions? How does it end up getting this collective behavior of all the cells moving together? So this is what we wanted to work towards. We're miles away from that at the moment. But the first question we asked is, okay, let's have a layer of active material, which is fixed in a layer. So in space, it stays 2-dimensional. And let's ask, if we allow the director field to point out of the plane and we allow flow out of the plane, what happens? So director field and flow can be 3-dimensional, but all the nematogens are fixed. The plane itself, the simulation plane, is fixed as 2-dimensional. And this is what happens. We were surprised. This is the fraction of nematogens, bacteria if you like, pointing out of the plane as a function of activity. If we have contractile activity, nothing points out of the plane. Everything stays horizontal. If we turn on the activity, the number of bacteria pointing out of the plane increases. So extensile activity drives things out of the plane. We did a linear stability analysis to look at that. This omega is the rate at which perturbations grow. The perturbations have a wave vector q, which is at an angle theta to the director. This is the rate of growth of perturbations in the plane, and you can see that it goes as cos 2 theta. So if I have an extensile system, this will be a growing perturbation for theta is 0. Theta equals 0 corresponds to a bend perturbation. Whereas if I have a negative activity, a contractile one, this will grow for theta equals pi by 2, and that corresponds to a splay perturbation, so that all works. For the perturbation out of the plane, you've got a cos squared theta here, and so you only get things growing out of the plane if the activity is positive, if you have extensile stress. Okay, so these things point out of the plane, but it's not just that simple. If you look at the configuration of the director, so we're looking at a flat plane here, and the white bits of the plane have a director pointing normal to the plane, or at least almost normal to the plane. And in the black bits, things remain in the plane. So it's not just random. You get the director field staying in the plane in these long, thin, snake-like configurations. These are dynamic. I'll show you a movie in a minute. They continually grow and they break, and then the tiny ones tend to pop up, so that you end up with a fixed number, a number which increases with increasing strength of extensile activity. These blue dots are twist defects, and we'll have a little bit more of a look at those. The ends of these things correspond to twist defects. So let's look at a movie of that. Here's a movie of these snakes moving around. They tend to grow As they grow, they start to bend, and then they tend to break at the positions where they're bent. So what I want to do now is look a bit more carefully at the director field and at the velocity field in this system to sort of see a little bit more what these snakes look like. Here's the director field in front of one of these long in-plane regions. The in-plane director points along the snake, and then at the edges it has to tilt upwards because outside the snake, the director is normal to the plane. And so what you get left with at the ends of this structure are places where you have a twist defect, where things move from inside the plane and then turn around and point out of the plane. The flow field, which is caused by this particular setup, is a flow field which goes outwards along the snake, and so it tends to elongate the snake. So here's a snake with the flow field pushing it outwards and making it longer. And then in this region here, you have an extensile system with a pneumatic director lined up. An extensile plus pneumatic director lines up means that what happens is that you get a bend instability and the snake starts to bend. It bends more and more until when you get a really sharp bend, that corresponds to the formation of a two-dimensional plus a half and minus a half defect. And where the defects are, the director field finds it's much easier to pop out of the plane. You get an out of plane region here, and this thing divides up into two different snakes. So then, just by chance, I saw a paper, a very nice paper from people in Japan yesterday, which shows you a plane of bacteria where the blue bits are bacteria which point out of the plane, and the other bits are bacteria in the plane. The yellow bits show bacteria in the plane. And you can see that, again, you get very much these snake-like structures. And although they didn't say it in the paper, I think they do have twist-like defects at the end of these structures. So maybe they have a different explanation, and so there's going to be fun trying to sort this out. Okay, so that's sort of starting from 2D and moving in 3D. What about now? Let's do active systems in 3D properly. And let me start by showing you a very nice movie from the Dogic group. This is a three-dimensional active system. Topological defects are replaced now by disclination lines. The lines are only allowed to start and finish on surfaces or to join up, and so you end up with loops. And these loops can be created and they can be destroyed. So here's a loop. In a minute, we'll see a loop dynamics. This is microtubule motor mixtures in these experiments. And this is the first time anyone's really done experiments on a fabricated 3D pneumatic. But whether or not biology is 3D pneumatics is something which is still a question. So here's a disclination line. And if I look at cross sections of the director field across the line, so this is a cross section of the director field. Okay, so these are sort of tilted towards you rather than actually, they're really meant to go backwards into the slide. The cross section either looks like a minus a half defect, or it can look like a plus a half defect, or in the middle, it can look like a twist sort of defect where things tilt up out of the plane. So you might expect that in contractile systems where you don't get flow out of the plane, you tend to get plus and minus a half defects, which stay in the plane. Whereas in extensile systems where the flows push you out of the plane, you see more the twist type defects. And indeed, if you measure the director field across this cross section, this is exactly what you see. You tend to get wedge type defects in contractile systems and twist type defects in extensile systems. But what we wanted to do was something a little bit different. We wanted to take this 3D stuff and put it 3D active pneumatic in a droplet and look at the interactions between the disclination lines and the droplet. And the droplet is just held as a droplet by surface tension, which isn't infinite. And so the droplet can change shape. And what we found is that the sort of shapes that we got, it mattered a lot whether this droplet, whether this active material was extensile or contractile. What we found was that if you have an extensile droplet, the surface anchoring of the pneumatic tends to be in plane. Whereas for a contractile droplet, the surface anchoring tends to be normal to the plane. The reason for this is just this: gradients in the director field give you flows. Across the boundary of the drop, the director field is changing from a finite value inside to a 0 value outside. Its magnitude is changing, that still counts. And so you get stresses at the surface. The stresses produce flows, and for extensile flows, it pushes the director to tend to lie in the plane, whereas for the contractile flows, the director tends to be normal to the plane. So now I'm just going to quickly show you 3 different possible shape changes that happen in these systems, which depend on extensile versus contractile and large contractile drop versus small contractile drop. So here's the first one. This is an extensile drop. And is this one the movie? Yes. And in the extensile drop, what you get is arms sticking out. Arms are formed. They're not very good arms, and this is just a computational problem that we have a diffuse interface, so it's hard to get very narrow arms and good resolution. But we can show that the arms form at disclination lines. What happens is that you get disclination lines forming across the across one of these arms. So like this, the flow fields around something like this are outwards because it counts as a plus a half defect. And so it pushes the arms outwards until the defect escapes from the end, and then the arm falls back. And in fact, this has actually been seen. They have much better arms here because it's an experiment, and so the length scales are much better. In the original experiments, they found arms being pushed out at the positions of plus a half defects. This is, again, a microtubule motor experiment from the Dogic group. So extensile systems gives you arms. Contractile systems, on the other hand, are a bit more tricky. Contractile systems like to have perpendicular alignment at the surface, but they're going to be places where the disclination lines cross the surface, and where they cross the surface, the closest you can get to perpendicular alignment is one of these twist defects. So you have in-plane regions, which are miserable, and what happens is that the defects point to each other so that you get in-plane lines between them, because this minimizes the regions where you have the wrong anchoring. And then flows are produced at those lines, and what the flows do is push the drop outwards, so you end up with this walnut shape. Here are the lines joining twist defects on the surface, and the flows are pushing these outwards. And so if we look now at the movie, this is probably the best one to look at. The blue dots are where defects hit the surface, the lines joining them create flows which push them outwards. If you have a tiny contractile drop, Again, you want normal surface anchoring in a contractile drop. But this is really miserable because then in the middle you have a huge energy because you have a hedgehog-like defect. So very quickly this system reorganizes itself so that you have a band of in-plane anchoring around it. The band of in-plane anchoring causes flows, and these flows push material up and down. And so what happens very quickly is this drop invaginates, and you get invagination just like in gastrulation. And you end up with a shape like this, entirely just due to active flows. So let me finish by just showing you what nature can do. They can still do things much, much better than we can. Again, to emphasize that flows are changing the shape of active entities. And this is what we're aiming for. This is actually the fly embryo growing to try and understand what's happening in systems like this. And what we plan to do next is put in cell division, which counts as a source of extensile activity. And also surface tension is probably not the best way of modeling these biological systems. We want very low surface tensions, but higher curvature energy to stabilize things. So that's the summary, and thank you very much for listening.